Hello, my name is Heiko Kociolek, and I'm presenting you today an experiment report on resilient IoT edge computing. This is joint work with Stan Grüner and Julius Rückert, and we're all from ABB Research in Germany. In our work at ABB, we're looking at the application domain of industrial automation, and so we collect data from, for example, a chemical plant like here, and then we run it through statistical algorithms, and then we visualize it in for example, mobile applications or via cloud backends. The setting looks like this. ABB has a lot of sensors, actuators and controllers installed in various application domains inside industrial plants, process plants, and the data from these devices is collected through an edge node. And the edge node does some local processing, so it can do stream processing, it can already do some visualization tasks, and then forwards also most of the data to the cloud for more resource-intensive processings. And one important component of the edge is obviously a message broker that relays all these different messages from the devices to the cloud. So we looked at that in more detail. And here's the conceptual architecture of our setting. Specifically for more resilient IoT edge computing, we looked at clustered MQTT brokers. That means you not only run one instance of a broker, but you run multiple instances on different host nodes. And this allows you to even continue messaging in case of one of the host nodes fails. There are also other failure scenarios. The internet connections between the publishers and the brokers may fail. Then the brokers itself may fail due to competing workloads or some bugs. There might be network splits inside such a edge cluster. And then there might be also, of course, connection problems on the subscriber side. In such a setting, which is visualized here in a very reduced form, of course, we can have thousands of publishers and thousands of subscribers, and there can be a large number of broker instances depending on the size of the cluster. Our dependability requirements in this area relate to availability. That means that the clients, that both the publishers and subscribers, can always reconnect to a running MQTT broker, even if one of the host nodes goes down. We looked at reliability. That means we don't want to have any message loss from the MQTT brokers, because for an industrial automation setting, there can be safety critical messages, like for example, a plant shutdown, and these messages must not get lost. And then we're also looking at message consistency, so we don't want to have any reordering of the messages, because that then can interrupt the optimization algorithms that utilize these messages. So based on these application settings, we decided to do a few experiments, both with open source and commercial clustered MQTT brokers, to find out how resilient they are to failures.
My name is Stan Grüner, and I would like to discuss how we test the resilience of the brokers. So our hardware setup is a starting X-based cluster having two servers, which run a cloud-native stack based on Kubernetes and Docker. We also use Ceph persistence as a persistent volume storage. We are testing 4 brokers: HiveMQ, MQX, VernMQ, and Mosquito. The first 3 brokers are cluster-based. Mosquito is not cluster capable. We have written a set of own tools, which we call Mayhem, which is a Python-based tool where we're able to create experiments of typically 1 sub-publisher and 2 subscribers, which connect to the broker on the test. We exchange around 5,000 messages and track and analyze them later. And we also repeat the experiments about 20 to 50 times. We are able to observe broker behavior using Kubernetes APIs and also proprietary broker APIs, for instance, to monitor the deployment to the hardware nodes. And we're also able to inject failures, for instance, provoking a hard or a soft kills of a respective broker instance. So let us continue with an overview of the practical resilience variants for the scenarios of host or broker failures. The first variant is to use a single instance broker with a distributed persistence. It means that even though the broker is run as a single instance without using the cluster capability, we are using persistency support of the broker, so it is able to store and restore its queue and other information on a persistent volume provided by Kubernetes. And since we are using Ceph as a distributed persistent storage backend, in case of a host or broker failure, the persistent volume is moved and saved by the Kubernetes system. The second version is to use the clustered capabilities of the broker. So in contrast to the first version, only 2 clustered brokers out of our tested setup are supporting those. So here we are running 2 instances of the brokers using an external load balancer. They appear to be 1 broker to the external clients. So this is implementing a cold spare tactic. However, there is no synchronization between the brokers or their queues. We can improve the second variant by introducing a cross-broker synchronization in terms of the communication between the broker instances within the cluster. So here the message is acknowledged to the client as soon as it is replicated at least once within the cluster. So from this more complex scenario, we expect some delivery delays and other penalties because of the complex cross-broker synchronization mechanisms. It also worth to mention that from the tested 4 brokers, only HiveMQ supports the synchronization feature, and the queue synchronization is not available in the public or open source version of HiveMQ.
My name is Julius Rückert. Let's now have a look at the results of our experiments. For all of the experiments, we tried to provoke failure scenarios and wanted to see how the different variants can cope with those. The first set of experiments deals with single instance brokers with persistency. Here we saw that both Mosquito and HiveMQ didn't show any message loss over all of our experiments. We saw some duplicate message deliveries, but this is not a big problem because we are talking about MQTT QoS1 message delivery here. When we looked at WernMQ and EMQX, we saw a different picture. For both systems, we saw experimentation runs where we didn't see any message loss as expected, but we also saw a part of the experiment runs that had a lot of message loss. The reason for that is different for both systems, and we looked into that closer and documented also our findings in the paper. In a second set of experiments, we looked into clustered brokers without queue mirroring. EMQX and WernMQ are 2 example systems that fall into this category. HiveMQ implements queue mirroring, and we disabled the feature for fair comparison here. We distinguish between graceful and ungraceful termination scenarios because we wanted to understand if brokers benefit from a graceful termination in a Kubernetes environment. We learned, however, that this is not the case. All brokers in all of the settings experience message loss. In an ungraceful termination scenario, we saw that EMQX and WernMQ even experienced reconnection problems where subscribers were not able to reconnect to newly spawned instances of the broker after termination. For HiveMQ, we observed another interesting effect where subscribers experienced message loss that were not directly connected to broker instances that were terminated. This brings us to the final set of experiments we want to share today, which is the clustered broker with queue mirroring. HiveMQ is the only example of a system that we found that implements synchronized message queues. The expectation would be even if we terminate individual instances of a broker with queue mirroring, all messages should arrive at the subscribers. For 19 out of 20 experiments that actually was the case in the case of HiveMQ. Unfortunately, we had some experiments, and here it was 1 experiment out of 20 where we saw unexpected message loss. With that, let me conclude our today's presentation by highlighting 2 key learnings we had. The first is that brokers that promise to be highly available cannot guarantee to avoid message loss in all times. This is important to consider when designing applications. Secondly, there's no one-size-fits-all solution when it comes to the selection of brokers. So we really saw that IoT applications have a very different profile when it comes to requirements towards messaging. So application designers should really take care of choosing a broker that fits their needs. And with that, I would like to conclude and thank you for your attention in the name of all authors.